Welcome back to Advanced Skills Learning. Gen AI prototypes are easy. Production systems are hard. In this video, we're going deeper into one of the most important architectural upgrades in real RAG systems, multi-index retrieval. If your system feels inconsistent as data grows or accuracy drops when you add more documents, this pattern is often the missing layer that explains why your system works in demos but fails in production. Most RAG systems begin with a single index. All documents go into one vector database, and every query searches the same space. At small scale, this looks clean and simple, but as your data grows, different document types start competing with each other. The system cannot distinguish intent effectively, and retrieval quality begins to degrade in subtle ways that are hard to debug. The core issue is that not all data behaves the same. Logs, FAQs, structured records, and long-form documents have very different characteristics. When you embed them into a single space, their representations interfere with each other. This creates noise, where irrelevant results rank higher than useful ones, and top-K retrieval becomes unreliable even when embeddings are technically correct. Multi-index RAG solves this by separating your data into multiple indexes. Each index is optimized for a specific type of data or retrieval strategy. Instead of forcing everything into one space, you organize retrieval around intent. A query is first analyzed, then routed to the most appropriate index, or sometimes to multiple indexes, before results are combined into a final answer. In practice, different types of indexes serve different roles. A dense semantic index captures meaning and is useful for conceptual queries. A keyword or sparse index is better for exact matches like error codes or identifiers. A structured or metadata index helps filter based on attributes like time, category, or source, giving you precise control over retrieval behavior. The effectiveness of multi-index RAG depends on how you split your data. You can separate based on intent, such as troubleshooting versus explanation. You can separate based on format, like logs versus documentation, or you can separate based on retrieval method itself, ensuring each index is tuned for how queries should interact with that specific type of data. The most critical component in this architecture is the routing layer. Every query must be evaluated before retrieval begins. The system decides which index to query, or whether to query multiple indexes in parallel. This decision directly impacts accuracy, because even perfect retrieval from the wrong index still produces incorrect answers. There are multiple ways to implement routing. Rule-based approaches use patterns or keywords to direct queries quickly and cheaply. LLM-based routing uses a model to classify intent dynamically, which is more flexible but slower and more expensive. Many production systems use a hybrid approach, combining rules for speed with LLM reasoning for complex cases. Quick check. 2 seconds. Which improves accuracy most? A. Better routing. B. A bigger index. C. Increasing top-K retrieval. Keep your guess. The correct answer is A. Better routing. Because retrieval quality is not about how much data you search, but whether you search the right subset of data in the first place. Once routing is complete, retrieval happens. Some systems query a single index, while others retrieve from multiple indexes in parallel. The results are then merged into a unified candidate set. Often, a reranker is applied at this stage to reorder results based on relevance before passing the final context to the language model. Multi-index architectures improve accuracy by reducing noise. Each index contains a more focused set of documents, increasing signal density. This means retrieval results are more relevant and aligned with the query intent. Instead of competing in a crowded space, documents are evaluated within a context where they actually belong. Consider a production system with 3 indexes: logs, documentation, and FAQs. A troubleshooting query is routed primarily to the logs index. A conceptual question goes to documentation. A quick clarification is answered from FAQs. The system may combine results, but each index contributes only what it does best, improving both speed and accuracy. Quick check. 2 seconds. What happens when routing fails? A. Does it increase latency? B. Cause wrong answers? C. Break embeddings? Keep your guess. The correct answer is B. Wrong answers. Because if the system queries the wrong index, even perfect retrieval returns irrelevant context, and the model confidently generates incorrect responses. Multi-index RAG introduces trade-offs. You gain accuracy, but increase system complexity. Routing becomes a critical dependency, and mistakes are harder to debug. You also need to manage multiple indexes, pipelines, and possibly higher infrastructure costs. This makes observability and evaluation much more important in production systems. You should consider multi-index RAG when your data is diverse and heterogeneous. If different queries require different retrieval strategies, a single index will struggle. This pattern is especially valuable in enterprise systems where logs, structured data, and documentation must all work together to produce accurate answers. Here's the key idea: one index is simple, but hides complexity inside retrieval noise. Multi-index systems expose that complexity and give you control over it. Routing becomes the brain of your system, and separation becomes the foundation for accuracy. In real Gen AI systems, this shift is often what moves you from demo to production. If you're building RAG systems, don't just scale your index. Think about how your data is structured and how your queries should be routed. That architectural decision will have a bigger impact than most tuning techniques. Thanks for watching. If this video helped, like the video and subscribe to Advanced Skills Learning for more Gen AI explainers, practical architectures, and quick quizzes to test your understanding.